A little while back, I made a video about this, the 10-cent Poya PY32 microcontroller. In that video, I mentioned that the PY32 wasn't the only ultra-cheap flash-based microcontroller, but there's also the WCH CH32V003, which also comes in around 10 cents, and it seems to be far more popular. Many of you left comments on that video discussing the merits of the CH32, and that got me wondering, did I make the right choice when I bought 500 of the PY32 for my latest project? Well, there's really only one way to find out. This is a development board for the CH32V003, which is the cheapest of the CH32V series, and it's the most comparable to the PY32F002A that I'd talked about previously. I'm going to put this through its paces and determine which of these you should use if you only have 10 cents, and you ignore the cost of passives and the circuit board and everything else you need to get started. Let's get into it. I'm Zach, and you're watching Zach of All Trades. I'm going to get started by discussing the biggest and probably most controversial difference between the PY32 and the CH32, the processor core. Specifically, the differences between the RISC-V core in the CH32 and the ARM Cortex M0 Plus core in the PY32. RISC-V, which stands for Reduced Instruction Set Computer, 5, is a free and open source instruction set architecture. For background, an instruction set architecture defines how the processor should behave with respect to software by outlining the things like instructions, registers, and memory handling. Binary code that is written for one processor should work on any processor that follows the exact same ISA. Now let's contrast this to the Cortex M0 Plus core. The M0 Plus is intellectual property from ARM, which is a for-profit company. And it's more than just an ISA, but it also includes things like hardware models, physical IP, and stuff that gets you much closer to actually building the chip on silicon. You also are going to get software tools and simulation tools. Now, when you buy a Cortex part, a fraction of what you spend goes back to ARM in royalties. Okay, I am assuming here that whoever makes the chip has properly licensed from ARM. There have been instances where foreign companies have stolen the IP. While I can't be 100% sure that Poya is licensing the devices correctly, they do show up in Keel Microvision, which is an IDE that's released by ARM. It seems a little unlikely to me that ARM would knowingly add microcontrollers to their software if they weren't properly licensing them. So then what do the makers of RISC-V chips do for their hardware designs? Well, most commonly it would seem that they develop their own proprietary implementations, which is what WCH has done here with the CH32 and their Shinki core. Hope I'm pronouncing that right. There are other open source implementations, including Verilog descriptions, and that's pretty cool. In all honesty though, I don't know that this matters for the majority of hobbyists. We're not likely to be making our own silicon, although that day is approaching. You can implement these Verilog descriptions on FPGAs, but that's probably more of a learning exercise than something you'd regularly do. Another point I'd like to make is that microcontrollers are far more than just their processor cores. They also have memory, peripherals, power systems, clocks, and so on, and those can actually be more important than the core itself. The ARM versus RISC-V debate doesn't actually tell us anything about these peripherals, and the majority of time these aren't going to be open. The differences in peripherals also means that programming various RISC-V or ARM parts, even with the same core, can be very difficult, as there's not really any standardization of these. Finally, I don't believe the underlying core makes all that big of a difference from a programming perspective, since most of us are probably writing our code in C or a higher level language. If you want to multiply two numbers, you're probably not worrying about loading values into registers, finding the right instructions. You're just going to type C equals A times B, semicolon, and move on with your life. The compiler handles the rest, and it's going to abstract away many of the differences in the underlying hardware. Now don't get me wrong, I'm a huge fan of open source. I definitely prefer not to pay corporations for software that hasn't really changed functionality in decades, looking at you, Microsoft Office. And I refuse subscription-based software. Much of the software I use on a daily basis is open source, and I contribute when I can. I also believe RISC-V is an important development that will have a really positive impact on the industry. But from what I've seen so far, I don't believe that RISC-V microcontrollers have a really substantial edge over ARM devices. At least not yet. For one, the CH32 is different enough that you'll need different software and different programmers, and that adds to the cost, and it can have a fairly steep learning curve. And despite not requiring royalties, RISC-V parts don't seem cheaper, at least not for the parts I'm comparing here, but I'll get to cost in a second. What I do think is awesome about RISC-V, and one of the reasons I'm really excited about it, is that it will allow companies, researchers, and even hobbyists to freely implement processors where they probably wouldn't have otherwise bothered. I foresee companies making more ICs smart as adding a processing core to a ADC, an IMU, or a radio, whatever, that'll no longer require that company to involve their lawyers and write contracts and pay fees just to license that core design. The benefits for academia will also be huge, not just research purposes, but also because students now have an actual open source ISA to study when they're learning how processors operate. I think there are also benefits on the 64-bit processor side for application processors as well as personal computing, but I'm not as familiar with that, and it's outside the scope of this discussion. That's all I'm going to say right now about core differences, but at the end, I'll bring this full circle and give you my thoughts. When choosing a microcontroller, or any other component for that matter, cost is only one part of the broad picture. Ease of use, availability, support, tool chains, total BOM cost, ease of assembly, part lifetime, and so on, are all things you need to consider. So when might you actually want to use one of these 10-cent microcontrollers versus one of the more expensive options? First, I personally believe that these chips only make sense if you're using them on your own circuit boards. If you're looking to just buy a development board for a one-off project, then I couldn't recommend either of these. For reference, I got this development board as part of a larger package on Amazon. It came with this, a CH32V003 development board, a WCH Link E programmer, and 5 each of the chips from both of these boards. And this was all $27. I put a link down in the description if you're interested, and I can attest that these work fine, at least to the extent I've tested them. Now, while I wouldn't say this is a terrible deal, and there are certainly cheaper options, especially if you go from overseas vendors, there are lots of options from other more reputable companies in this price range, and they're certainly easier to use, and they're going to have more features. The STM32 Blue Pill, or the Nucleos, the ESP32s, any of the Arduinos, the Raspberry Pi Pico, I think that these, and really any of the popular development boards, are going to be better choices. So one use case for these 10-cent parts could be to save money when you're building a product you're going to sell. Although honestly, I'm not sure I'd feel that comfortable doing that either. I would worry that one of these manufacturers might suddenly stop making these, which would invalidate much of the non-recurring engineering you had done. Also, if I opened up some product I'd bought, especially something I expected to have a long life, and I saw one of these ultra-cheap chips in there, I'd be a little put off. Personally, if I were making something I planned on selling, I'd spend a little more money from a part from ST or Texas Instruments or Renesas. One of the parts I could just buy from DigiKey and be reasonably assured it'd be around for the next decade. Now, where I do think these microcontrollers are really useful is for projects where you need a lot of microcontrollers that are doing pretty basic tasks. This is what I'm doing with the PY32 in my Tile Backsplash project. Here, I'm using the internal ADC on the PY32 to digitize a microphone signal and communicate the peak value back to a main processor. I need about 250 of these, so for a personal project, I just really can't afford to use anything more expensive. Check out the video on that project if you haven't, and subscribe so you can be sure to catch the rest of it. These types of projects, things like making an analog sensor into a smart one, doing at-the-sensor processing or event detection. Heck, even making your own personal computing cluster. These are the cases where these ultra-cheap microcontrollers shine. So I've called these both 10-cent microcontrollers. But how accurate is that? For comparison, I'm only looking at the lowest spec, cheapest parts, which are the CH32V003 and the PY32F002. And these prices are as of mid-2024. On LCSC, which I consider to be a reliable vendor, you can buy the PY32 for between 13.5 cents and 17.5 cents if you buy only 5, and 8 cents to a smidge over 11 cents if you buy 500, depending on the package. The CH32, in comparison, is on the order of 19 to 23.5 cents for 5, and 12 to 14.5 cents for 500. Additionally, as of right now, you can't even order 500 of a single type of CH32 because there are only 415 SOP8s in stock and 100 QFN20s. For the PY32, on the other hand, all 5 options are in stock, and the scarcest one has over 4,500. Now, I know that you can buy the CH32 on AliExpress from the official WCH store. In fact, you can apparently get 50 of the 8-pin CH32V003 chips for a single $1 shipped, which is absurd. But that's a one-time deal, and you don't have much control over quantity. I am also personally far less comfortable ordering from AliExpress, but you could feel differently about that. So from a cost and availability perspective on bare chips, I have to give the advantage to the PY32. If you're looking for development boards though, then the exact opposite is true. There is this board for the PY32F003 on LCSC right now. It costs about $14.50, which is a bit high for what you're getting, and I've noticed that the price fluctuates considerably. There are a couple other options for the PY32, but they have no reviews and probably no documentation. The CH32 though, like I said, I got this on Amazon, delivered in 2 days with the spare chips. It was a little pricey at $27, but very easy to order. Check out the description for the link. There's also plenty of other cheaper options for the CH32, particularly from overseas. Just Googling CH32V003 will turn up lots of options. So for development boards, I've got to give the edge to the CH32. Taking a look at the datasheets, you'll find that there's really no clear winner, as the PY32F002 and the CH32V003 trade blows in different areas. Now allegedly, the PY32F002A uses the same die as some of the higher end parts, and you can unlock additional features if you know what you're doing. But that's not guaranteed. That might not always be true, so for this comparison, I'm sticking strictly to what is advertised. To start, the CH32 can run up to 48 MHz, and it has a PLL that can make that frequency from the 24 MHz internal oscillator. The PY32, though, runs at half that. 24 MHz, it has no PLL. The PY32 does have the edge for RAM and flash, with 3 kilobytes of RAM and 20 kilobytes of flash, whereas the CH32 has 2 kilobytes of RAM and 16 kilobytes of flash. Both parts have one advanced timer and one basic timer, but the PY32 has an additional low-power timer. Both have ADCs, however the PY32's is 12 bits and the CH32's is only 10. If you're sampling that data really quickly though, you don't want to load up the processor, then you're going to find the DMA on the CH32 very useful, but you don't get on the PY32. The CH32 also has a built-in op-amp, which, if you need it, could reduce your bill of materials in comparison with the PY32. For connectivity, they both have one UART, one SPI, and one I2C, but there's a caveat for the CH32. The SPI is only broken out on the 20-pin packages. There's no SPI on the 16 and 8-pin options. Compare that to the PY32, where you get the option for all 3 regardless of package. If you have an application in mind though, you should probably check out the multiplexing on those really small packages, as some of those functions overlap. Other than that, these 2 parts are really similar. They can both operate at 5 volts, they both have comparable package options and number of I/O, and they have similar low power modes. As you can probably see, It is hard to declare one of these better than the other without knowing your exact application. On one hand, the CH32 is faster and has DMA and that built-in op-amp, but the PY32 has more flash and RAM and a higher resolution ADC. The datasheet's one thing, but how do these chips actually perform in the real world, and how easy are they to use? For the PY32, go back and check out my previous video, where I walked through setting up the IDE and then did 2 coding examples. Now the PY32 has pretty much no information online, and there really aren't any tutorials, which is definitely a drawback. So in the previous video, I went into quite a bit of detail on how to use them. There is much more information for the CH32 though, so I'm not going to walk through this step by step like I did before. What I am going to do is replicate the 2 test codes I did in the last video. First, I'm going to blink an LED using a timer and interrupts. And then secondly, I'm going to read an analog voltage with the internal ADC and report it to a computer over serial. I'll then compare the experience on the CH32 with that of the PY32. For IDE, I'm going to be using Mound River. This is what is recommended by WCH, which is why I'm choosing it, similar to what I did for the PY32. There are other IDE options, probably better options. There's even support for the Arduino IDE, so don't be too scared away by this. Mound River is Eclipse-based, so it's going to feel pretty familiar if you're coming from something like the STM32 Cube IDE. As mentioned, the boards I'm testing this with came from Amazon and included 2 development boards, one for the CH32V003 and one for the V203, as well as 10 bare chips and the WCH Link E, which is this comically bulky USB programmer that you can't actually push the buttons on without removing the case. There's also a GitHub repository I've linked that has lots of information on this chip and this board, things like the schematics, example code, some how-to PDFs. I recommend you poke through that before you get started. When you open Mound River and go to create a project, you basically just need to provide a name and select the chip you're using. Click OK, and that's it. All the start code and the HAL drivers are there and ready to use. The start code sends the system clock rate and the chip ID over UART, as well as has some UART echo functionality. Without making any changes to the start code, I compiled and flashed it just to verify that this at least worked. I used the serial adapter built into the Link E, as well as MOBA Xterm on a PC. All I had to do was connect 3.3 volts from the debugger to VCC on the board, ground to ground, SWDIO to PD1, and RX to PD5. This would have worked great, except my Link E firmware was ever so slightly out of date, so Mound River refused to use it, and it forced me to update it, which I tried to do itself. Halfway through the update process though, the Link E disconnected from my computer and didn't come back. Now those of you that deal with these things regularly know that this can be a bad situation. A little searching though led me to the WCH Link utility, which is available straight from WCH's website. This luckily recognized the Link E, and I was able to update it without much trouble. Back over in Mound River, the program now flashed correctly, and the serial communication to my PC worked as it should. I then got started modifying the code to blink an LED with a timer. This was pretty straightforward, and honestly pretty similar to the PY32 or any other ARM part. You configure the timer, start it in the appropriate mode, configure the LED GPIO pin, write an interrupt handler where the pin is actually flipped, and then you call the initialization functions from the main function and enter an infinite loop. Interrupts will do the rest. Interestingly, the CH32 development board doesn't actually connect the LED to a pin, unlike what you would usually see, so you get to choose where it goes. The downside though is that this does require a wire on the development board, which might not be desirable for your final application. I did have one issue and a couple of complaints. The issue I ran into is in regards to attributes on the interrupt handler function prototype. I'm not going to go into great detail here, as I wouldn't say that I fully understand it myself, but the crux is that if you create an interrupt handler, and the WCH interrupt fast attribute is applied to the other interrupt handlers, then you should go ahead and apply it to the one you create as well. I didn't, and my initial code ended up in the hard fault handler. Luckily, since this microcontroller is fairly widely used, I actually found a discussion and a solution for this issue online. My complaints are in regards to the documentation. The datasheet, the reference manual, there's a core manual, and a bunch of other how-to guides. They're really well written, and they're written in English, unlike what you get for the PY32. But I could not find any documentation for the hardware drivers, despite the fact that they're used by default in Mound River. Now, to be fair, Poya also does not have documentation for the drivers on the PY32, but those drivers are basically just copied from STM32s, so ST's 2000-ish page HAL manual is directly applicable. For the CH32, I basically didn't have any guidance other than the reference code and reading through the drivers in the IDE. Now I know roughly what I'm doing, and the drivers behave pretty similarly to the ARM devices. They mostly just differ in syntax. So I was able to stumble through this by just using the IDE's autocomplete functionality and kind of just guessing what the function should be. But still, it would have been really nice to have a manual. If anyone knows that one exists, please let me know. Now this brings me to another minor complaint. This is regarding the reference code. The reference code provided on GitHub is quite complete. It covers every peripheral, but I found that it only covers more complicated use cases. Take the timers, for instance. There's an example code for DMA, for encoder counting, for output compare, one pulse mode, etc. But there's not an example that just covers setting up a timer to generate an interrupt. The ADC is another good example. There is no code that just covers a single software start conversion, which is probably what most beginners, the ones who are reading the example code anyway, are trying to do. You can certainly piece together what you need from some of the more complicated examples, but I found this a bit odd. Regardless, I worked through this Blinky example reasonably quickly, and I got the board to blink its LED 500 milliseconds on, 500 milliseconds off, without much trouble. This was certainly faster than getting the PY32 running, even when you take into account updating the link E. On to the more complicated example, reading a voltage with the ADC and sending it over serial to a computer. Setting up the UART here couldn't have been easier, literally, because it's already done for you in the start code. There is a debug file included. You can go through and check out the exact functionality, but one thing it does is redirects printf to UART1. All you need to do is know the pins, PD5 for TX and PD6 for RX, hook them up to the link E appropriately, and then printf just works. Compare this to the PY32, where I still haven't gotten printf to redirect correctly. I'm compiling messages and then sending them over the UART the manual way. The other main thing that needs to be done here is configuring the ADC. This took a little bit of playing around because of the aforementioned lack of documentation on the HAL drivers. Pretty simple stuff like, should this field be 0 indexed or 1 indexed, and how do I do a single conversion since all the example codes are multiple or injected conversions? Overall though, I would say that this example took me a similar amount of time to what it did on the PY32, with my lack of familiarity with the drivers being offset by the fact that the UART was already set up. So here's the circuit setup. I've just run VCC to one side of a potentiometer, ground to the other side, and the center tap of the pot to PD3, which is ADC channel 4 on this chip. This makes an adjustable voltage divider, and you can see here that as I rotate the pot, the ADC values respond logically, albeit only to 1023, as this is only a 10-bit ADC. The ADC noise seems quite small, only an LSB or so at 43 cycle sampling time. And I ran this for many hours, and I didn't observe any drift. So now that I've had the chance to test out both the PY32 and the CH32, including their functionality, native software environment, and ease of writing and flashing code, which chip is the winner? Well, I hate to reiterate what I've already said, but it really does depend on what your final application is for this chip, as they both have pros and cons, and they could make or break a particular project. But if they both have the features you need, then well, I have to give the edge to the CH32. It comes down to 4 things. First, when you download Mound River and you select the CH32V003, it pretty much just works. There's no messing around with configuration, no trying to load the right hardware libraries, really nothing other than needing to update the link E. After that, I literally hooked up the debug probe, compiled, loaded the start code, and that was it. It just worked. Second, and you might not personally care about this, but RISC-V is kind of cool right now, and by using the CH32, you're helping to support that movement. Third, I think I have to give the hardware edge to the CH32. It runs at twice the speed, it has a DMA controller, and I feel like that's probably a little more useful than what the PY32 has, which is additional flash and RAM, the higher resolution ADC, and an additional timer. You could debate this point though, so take that with a grain of salt. And finally, there's a lot of online help for the CH32. Not necessarily directly from WCH, but in online discussion and even a lot of tutorials. Now, the PY32 is very, very similar to the STM32, so STM's documentation, even for stuff like the HAL drivers, is very useful, but there's essentially no online help specifically for the PY32. That said, I did find the lack of driver documentation on the CH32 to be quite frustrating. So did I make the wrong choice when I bought these 500 PY32 chips for my tile backsplash project? I don't think so, and it all comes down to availability. Remember when I said that for the CH32V003 there were only 415 of one package and 100 of another package in stock? Well, I wrote that a couple days ago, and before filming this, I went back and checked again. Now there is not a single CH32V003 in stock at LCSC. And that's the problem. If you want 10, 50, maybe even 100 CH32s, then sure, you can probably order them on AliExpress. You'll probably get what you need. But if you need a whole spool of these, even just 500 of them, then you're out of luck. With the PY32 though, I've never had to worry about stock. Plus, it's not like one of these existing negates the usefulness of the other one. You can have and use both of them. I think that they're both fantastically useful microcontrollers. They're not all that different to program. They're both an insane value. And now that I've gotten experience with both of them, I'm going to keep them both in mind for future projects. That's all I've got today. In the next videos, I'll be getting back to some of the projects, so please like, subscribe, and check those out. Thanks for watching.